radicals. So when we simplify radicals, that's saying we're simplifying like the square roots. But we're going to be dealing with more than just square roots today. We're going to be dealing with higher powered roots. So just like you can square a number, or you can raise a number to a third power, or raise it to the fourth or the fifth, you can take and find more than a square root of an item. So what 3 cubed is 27. So if I take the third root of 27, I end up at 3. So it's the way to undo higher powers. Okay, so if I have 2 to the 4th power, that number is 16. It's 2 times 4, 2 times 2 times 2, 4 times, that's 16. So if I take the 4th root of 16, I end up at 2. And so we're going to work these the same way we did yesterday. We're going to be looking to see how can we simplify these radicals. Only things that I'm adding in new today, besides the index changing, is we're going to have some variables involved. And so the variables are actually easier because you don't have to find the prime factorization. The prime factorization is already found for you. So they're actually a little bit easier to work with. So let's take problem 1. We are having the 4th root of 112 b squared, or a squared b to the 6th. And so our first step is to simplify that 112. So 112 is divisible by what number? Which are the prime numbers? 2. Leaving us what?
56.
Which is divisible by? 2. Leaving us?
28.
Which is divisible by?
2, 14.
Which is divisible by?
7.
Well,
2.
2. Because we want to stay with the same number each time until we can't divide by that number anymore. So when we were dealing with square roots, we were looking for groups of 2. When we deal with higher powered roots, we're going to be looking for that index, which is a number up here, to tell us our group size. So we're going to be looking for groups of how many?
4.
4. So we have one group of 4 2s. And so that 2 gets to come outside the radical. Next, we're going to take our variables. Some people will need to see it written out, and eventually you may not. This right here is just a way to see it. So I'm going to expand out a to the 2nd power, which is just a times a. Is there a set of 2 a's there? Or a set of 4 a's, excuse me. No. So there's nothing that can come out of the a's. B, I have 6 of them. Is there a set of 4 b's? So I have a b that comes out. Now, this is where the variables get a little tricky. Is your index up here even? Is that 4 even?
Yes.
If it's even, you have to put absolute value bars around your variable unless you're raising it to an even power. So if you're raising it to the 2nd power, you wouldn't have to put it. And that goes back into the fact that if you take -3 and I square it, what is the result? Positive or negative? Positive. But if I take -3 and raise it to the 3rd power, it comes out negative. So I don't have to worry about the sign when it's an odd root. It takes care of itself with the variable. When it's an even root, I need to put those bars to restrict us to the positives. But if I have whatever number coming out and I square it, it takes care of itself. That's just I don't have to put it for any powers on that. And we'll do some of those here in a second. Now let's figure out what gets left behind inside my radical. So my radical is the fourth root. So what number gets left behind?
7.
A 7. How many a's get left behind?
2.
So a squared. How many b's get left behind?
2.
So b squared. Make sure your radical symbol, the index is in that check mark spot, and your bar covers everything that you have on the inside. That's your answer. On number 2, we're going to do the 7th root of 384, x to the 7th, y to the 9th. And so we need to simplify what's inside the radical first. So we're going to take that 384. And I will tell you this, especially on the higher powers, you're going to have a lot of 2s or 3s being what's being multiplied. Just because to get it to where it's small enough for you to work with, a lot of times they'll do those. If it's a larger number, you might see bigger numbers than that being worked with. So 384,
2.
what does that leave us?
192. And I can divide by 2.
Leaving us
96. And that can divide by 2. Leaving us with 48. And that can divide by 2. And that leaves us with 24. And that can divide by 2. Leaving us with
And-
can divide by 2. And leaves us with 6. And that can divide by 2. Leaves us 30.
And so it kind of gives a clue that we're going to have a lot of the same number because it had a 7th power. Or 7th index, excuse me. And so do I have a set of 7 2s? Do I have any extras?
No. A 3.
A 3 is extra, but not any 2s. So a 2 can come out. Now let's look at our variables. And I have x to the 7th. So how many groups of 7 do I have? Do I need to write it out to figure that out?
No.
Because if I have the index and the power match, it automatically comes out just once. Do I need an absolute value bar on this, do you think?
No.
No, because why?
Index is on.
The index is odd. Now, on y to the 7th, or y to the 9th. How many y's can come out? How many sets do I have?
1.
So I have one set of y's that can come out. And that's going to leave behind in my radical the 7th root of my 3 that gets left behind from my constant, or my coefficient in this case, and y squared. Now, is there a shortcut to get to what besides writing out all your variables? Anybody see a pattern that you can look for? Take your power on your variable. So let's take the x to the 7th. Take the 7 and subtract out your index. Does it go? It goes in evenly. That's a positive number when you do that. That means 1 can come out at least. And so like 9 minus 7. I guess it's 1 that came out and 2 that are left behind. So on this, we have a 4 as a coefficient in front. That 4 just hangs out until we're ready to work with him. So we have 4 times the cube root of 500 m to the 7th n to the 7th. So what do I do next?
You divide
The square root
the
first.
500.
Do the 500 first. What's that divisible by? 2. Leaving us 250. What's 250 divisible by?
2.
Leaving us,
125.
what's 125 divisible by?
3. 5.
5. Leaving us 25. And that's 5 and 5. So what do I have a set of?
2s and 5s.
Do I have a full set of 2s? 'Cause I need 3 of them. But I do have a full set of 5s. So a 5 can come out. And now let's look at our variables. So I have m 7 times, and same thing with n. How many sets of 3 do I have?
2.
So I have m squared. Will it be the same thing for n?
Yes.
What gets left behind? 1 m and 1 n. What gets left behind with the numbers, though?
2.
The 2's. So now we simplify our numbers and we end up with 20 m squared n squared. And we have 4 m n. Oh, and I forgot the index. This is a third index. And I'm going to do one real quick other one. Yes. And this one's not going to take long. We're just going to look at the variables. So let's say I have a 4th index of m to the 9th n to the 2nd. And so when I'm working this, I'm looking for m, and I'm wanting to see how many sets of 4 can come out. If you need to, this may help you. See how I set that up when I'm writing them out? I only went to 4 in each row. And that may help you see there's 2 sets. So that means m squared comes out. Actually, let's go ahead and make the n a 5, sorry. And so let's have n to the 5th. I have 1 set of n's that can come out. So that n needs to be in the absolute value. The m does not have to be. Because the m is squared. It doesn't have to be. That's going to leave behind the 4th root of mn. That's something that was giving them troubles in first period, so I wanted to make sure that y'all can kind of see how that worked.